Okay, so in today's lecture, we're going to be finishing off differential equations. So we'll go through the fourth method of solving differential equations using the Laplace transform, and then we'll do a couple of mixed problems. So some of the problems you can do it with separation of variables, some of them using the integrating factor. There's one where you can use two methods. We'll go through both. Like I said last time, if you come across a problem like that, then you'll get the marks for both ways. So if you can do it using separation of variables, and then you can do it again using integrating factor, you get your 10 out of 5 or whatever it is. Okay, so this is method number 4. Solving DEs using Laplace transform. Okay, so we're going to do a quick recap of what the Laplace transform is and some of its properties, and then we'll go through the method on how to use it. So a quick revision. Okay, so remember how it's defined. Given a function f, we define the Laplace transform of f as the integral from 0 to infinity e to the minus st f of t dt. Okay, so that's just from the definition. So once we do all the integration with respect to t, we're left with the function f of s, and usually we call that capital F of s. Okay, so if I give you the little f function, then the Laplace transform is that capital F function, but now a function of s. Okay, then there's a few properties. So we went over the proofs and stuff last time, so I'll just list them out. So the first one is the Laplace transform of f prime. This is s times capital F of s minus f at 0. Okay, we went through the proof with that. You had to do that integration by parts to find that. And then similarly, we can have the Laplace transform of f double prime. So here you just do the integration by parts twice, so very similar to the first one. This is going to be s squared f of s minus s times little f at 0 minus f prime at 0. Okay, so that was the second property. The third one, the Laplace transform of t to the n, right, for some exponent n. Okay, so t squared, t cubed, and so on. This is going to be equal to 1 over n factorial, whatever that exponent was, times 1 over s to the n plus 1. Yeah, that was quite easy to prove using bar parts again. Okay, then we had these two special cases with the trig functions. So that was the Laplace transform of sine omega t. Okay, this is going to be omega over s squared plus omega squared. Okay, again, you can use bar parts to prove that, but you won't need to know how to prove any of these. Okay, and then with this, we had the one with cos. Okay, so this was very similar, but instead of having the omega at the top, it was the s at the top. But the bottom parts are the same for both. Okay, then there were a couple more. So if we have t times f of t, so we know what the Laplace transform of f is if we multiply it by t. This is the same thing as minus capital F prime of s. Okay. So if we know what it is for little f, then we just take the derivative, put a minus sign in front, and that's what we get for t times f of t. Okay, and lastly, the Laplace transform of e to the at. This is 1 over s minus a. So just take note of these. We'll need this for when we do the inverse Laplace transform later on. Okay, so the method. Okay, so we'll do this with an example just to show you how we go through the method. So let's say we have a second order linear differential equation, something like a y double prime plus b y prime plus c y is equal to some f of x. Okay, we don't know what that is. Okay, that talking needs to stop. Okay, so a, b, and c, those are just some numbers in front. We don't know what they are. Second order linear. So this is very difficult to use for non-linear differential equations. But if you get something like this, then you can use the Laplace transform. And then on the right-hand side, that f, that can be any function. Okay, so the method, there's 3 steps to it. So step 1, apply the Laplace transform to both sides of the equation. Okay, so we've got this differential equation. You do the Laplace transform on the left and the right. Okay, and then we define the Laplace transform of y as capital Y of s. Right, very similar to what we have over here. So the Laplace transform of the little f, that became capital F of s. So here we just make the definition that the Laplace transform of y is capital Y of s. Okay, number 2. Solve for capital Y of s. Okay, so once we do the Laplace transform, all of the derivatives will go away, and we're just left with some equation for capital Y of s. Okay, so all the derivatives from the differential equation, they go away. We just solve for Y of s, whatever that might be. Okay, so just a note, all derivatives are gone. Okay, so we solve for capital Y of s, and then finally, step 3, apply the inverse Laplace transform to both sides. So the inverse Laplace transform of capital Y, that will just take us back to the little y, which is our solution. Okay. And then once you do the inverse Laplace transform, you get back your little y, which is the solution. Okay. So just 3 steps. So apply the Laplace transform, you get your capital Y, solve for that, and then apply the inverse. Remember what the inverse was. So say we get something like this in the expression. When we do the inverse, that will just be sine omega t. You just read it backwards. So if you get something like this, so say 1 over s minus 2, for example, when you do the inverse, it will be e to the 2t. Okay, so you just go backwards. Any questions on the 3 steps? Okay, let's have a look at an example. And again, it will be something like that second order differential equation there. Okay, example. Let's say we have y double prime plus y prime minus 2y is equal to 0. Okay, so something easy here. So all of the coefficients are just some numbers. Okay, so we got 1, 1, and minus 2. And then that f of x, we're going to start off with it being 0. Okay. Later on, we can change that. We can say it's cos x or sin x or x squared or something like that. But for here, we're just going to take f to be 0. Okay, so let's go through the steps. Number 1, we're going to apply the Laplace transform to the left-hand side and the right-hand side. Okay, but since the right-hand side is 0, we still get 0. Okay, now we know the Laplace transform is linear, so we can do it on each of the terms individually. So this will be the Laplace transform of y double prime plus the Laplace transform of y prime. And then the -2, that can also come out. So we have -2, the Laplace transform of y. Okay, so we have that. Now, for the first one, the Laplace transform of the second derivative, we go up a little bit. There we go. Second property there. So the Laplace transform of the second derivative is going to be that right-hand side. And then the second term here, that's the Laplace transform of the first derivative. Go up a little bit here. We see that's going to be this right-hand side here. Okay. One more thing to note. Over here, we see for the first and the second derivative, we got minus f at 0. And then at the second one there, f of 0 minus f prime at 0. Okay, what are those? F of 0, f prime at 0. What do we call them? Sorry? Okay, we covered it yesterday. So you have a differential equation with initial conditions. Yeah. Okay. So this f at 0, f prime at 0, those are the initial conditions that we have to then substitute. Okay. So let's write here. Inside here, let's put some initial conditions. Okay. So let's say y at 0 is 2 and y prime at 0 is 1. Okay. So we're going to have this differential equation there with those initial conditions. So y at 0 is 2, y prime at 0 is 1. Okay, so let's substitute the Laplace transform for these three. So the first one, that's going to be s squared y of s minus 2s minus 1. Okay, so that's for the first term, just substituting in. Then for the second term, it will be plus s y of s minus 2. Okay, that's for the second term. And then the last one, that's just going to be minus 2 capital Y of s. Okay. And again, notice how there are no more derivatives. So all we have left is this capital Y of s. Okay. So that's step 1. Step 2, we need to then solve for capital Y of s. So let's do that. Okay, so we're going to keep all of the y terms on the one side, everything else we take over to the other side. So those are all the terms with the y. We keep that on the left-hand side. Everything else we take over. So the minus 2s, we take it over. That will be a plus 2s. Minus 1 take over. That will be a plus 1. And then the plus 2. So plus 3. Okay. Now, for the first three terms, we can factor out the y of s. Okay, so we end up with that. And then finally, we can divide through by all of that, and we get y of s by itself. Okay, we end up with that. I can still hear talking. Okay, so we've got this capital y of s there. So step 2, done. We've got that function there. Step 3, we need to do the inverse Laplace transform of that right-hand side. But this right-hand side is a bit of a mess. What we want is it to look like these right-hand sides over here. Okay, currently it doesn't look like that. So what we can do is split this up into two fractions. And each of the individual fractions, we can then do the inverse Laplace transform. Okay, very similar to the partial fractions we covered last semester. So y of s is going to be equal to 2s plus 3 over, okay, and we're going to split it up into the two fractions. So we have to factor the denominator. So that's going to be s plus 2, s minus 1. Okay, just your normal quadratic factoring. Okay, then this is going to be some a over s plus 2 plus some b over s minus 1. Okay, I hope you remember your partial fractions from last semester. Okay, so now we need to solve for a and b. I'll let you fill in the details. So we're going to end up with y of s is going to be, for a, that ends up being a third. And b, that ends up being 5/3. Okay, right, you've done partial fractions enough, you can do that. So we end up with this. Now we look at the right-hand side there. We go back to the table we had earlier and see what does this match up with. So notice we have 1 over s plus 2 and 1 over s minus 1. So let's see what that goes to. Okay, so we go through our list. It's not going to be, it's not over 1 over s to the power something, right? It's not that one. There's no s squared, so it's not none of those trig ones. We see that very last one, 1 over s minus a. It's going to be that one. Okay, so let's look at the first one we've got. That is 1 over s plus 2. So we go back up here. So 1 over s plus 2, that must mean a is minus 2. Then we look at the other one. That's 1 over s minus 1. Again, compare it to what we have over there. So a must be 1. And then you just put that for the left-hand side. So step 3, y of x, that will be 1/3 inverse Laplace transform of this, plus 5 over 3 inverse Laplace transform of this. Okay, and then you just look at the table to see where it goes. So in the first case, we know that a was minus 2. So this is going to be 1/3 e to the minus 2x. Okay, and I'll make a note here. This was a equals minus 2 plus 5/3. And then this one was a equals 1. So that will be 5/3 e to the x. Okay, and that's our solution. All right. Any questions for this example? Yep. Yes.
What we're more or less using to find out the solar.
Yeah. It will be one of these. Yeah. So, yeah. This one. Yeah. It was y of 0 is 2, y prime of 0 is 1. So that's what we put over here for f of 0, that was the y of 0, and then the f prime of 0, that was the y prime of 0. Okay, any other questions? Okay. Okay, let's put some homework problems for you to try. Okay, number 1, y double prime plus y prime minus 2y, okay, equals x plus 1. Okay, so now that right-hand side is no longer 0. It's a bit more complicated, but it's not too bad. With y of 0 is 2, and y prime of 0 is 1. Okay, so you have to have some initial conditions with this. Okay, number 2, y prime plus 3y is equal to sine x, with y of 0 is 1. Now we see for example 2, that's a linear differential equation. So you can do it using an integrating factor, or you can do it using the Laplace transform. So you can do it 2 different ways. Okay, and then number 3, y prime plus y is equal to x squared. Again, it's a linear first order differential equation. So you can do it using an integrating factor, or you can do it using Laplace transform. So if you want your 10 out of 5, you can do it both ways. Okay, and then y of 0 is 3. Okay, so I'll just make a note here for these two. So this is first order linear. So you can use an integrating factor. Okay, but if you don't want to do it 2 different ways, you can pick one. That's easier for you to do. Right. Any questions about this Laplace transform method? Okay. So for the quiz next week and then the class tests and the exams, please expect something like this from these 4 methods. So again, I don't tell you which method to use. That's up to you. So if you want to use the Laplace transform way or the linear integrating factor way, you do whatever you want, but it will be mixed out of the 4. Okay, I won't tell you which one. Okay, again, any questions before we move on to the mixed problems? You're all good. Okay, so let's have a look at some mixed problems. Okay, so number 1, we have x, y, y prime is equal to x squared plus 1. Okay, so we have a look at it, see what type of equation, differential equation we have, and that will tell us which of the methods we can or can't use. So first of all, it's first order. Okay, so that makes things a bit easier. Secondly, it's non-linear, right? We've got y times y prime. So immediately method number 3 crossed out. We cannot use that. So we either check if it is separable. If it's separable, we can go ahead and do that. Or we can use the Laplace transform. Now, again, it's a product of y times y prime. Laplace transform will be very difficult, so we cross that out. So what are we left with? Separable. So we go with that. Okay, so that's the thinking you need to go through for these problems. You see what order it is, if it's linear or non-linear, will the Laplace transform be too difficult? And then, you cut down your list on what you can do. So we went through everything, so we go with separable. Okay, so what do we have to do for separation of variables? We need the y's on the one side, the x's on the other side. So this is going to be y dy is equal to x squared plus 1 over x dx. Okay, so we split it up, the y's on the one side, x stuff on the other side. Then we integrate. So we're going to have the integral of y dy is the integral of x plus 1 over x dx plus c. So we get 1/2 y squared is equal to 1/2 x squared plus the natural log of x plus c. Okay, at this stage in the year, doing these integrations, you should just be doing it, like second nature. If you have to think about 1 over x goes to log, you're being too slow. Okay, you shouldn't be thinking about it at all. So x, you just write 1/2 x squared. Don't even think about it. 1 over x, natural log. Again, don't even think about it. Right. Any questions for this one? Yeah. No, you don't need to do that. No. So you can leave it like this. That's perfectly fine. If you do want to write it as y equals something, and it's possible, you can if you want, but I'm not going to take marks away for that. Okay. No, so there's no initial conditions, there's no boundary values, so we leave it at C. Okay. Also, if you do try solve for Y, I can give you part marks for that. But if you just leave it like this and it's fully correct, you don't need to do any more. Okay. But if it's wrong and you do attempt it, I can give you some marks. All right. Yes.
How come when you integrate from the left-hand side, you don't plus C?
You could do a plus C1 on the left, a plus C2 on the right. Take all your constants to one side and call it C. It's the same thing. Okay. If you do want to put like plus C1 and plus C2, if that's better for you, that's fine as well. Okay. But at the end, remember it's first order, so there's one unknown. Okay, so that's C1 and C2, that ends up becoming just one unknown. Okay. Any other questions? All good. Okay, number 2. So here we've got x squared y prime plus 2xy equals the natural log of x. Okay, so let's go through the list. It's first order, so that makes things a little bit easier. Is this linear or non-linear? Linear. So it's linear, so we can use an integrating factor. That's fine. Is it separable? Hands up if you say it's separable. Hands up if you don't know what separable means. Okay. Yeah, no, it's not separable. You can't use separation of variables. Can we use Laplace transform? Who says yes? Who's going to get quiz 11 wrong? Okay. Yes, you can. You can use Laplace transform for this one. Maybe it's a hint for the quiz. I don't know. Okay, so you can use Laplace transform for this. It's a little bit difficult, but if you want to do it, you can do it. However, let's stick with it being linear. So it's first order linear. We can use an integrating factor. For homework, you can try the Laplace transform way. However, it is not in the standard form. Remember, standard form for linear is y prime plus py equals q. We don't have that. That's not here. So let's divide through by x squared. So we're going to have y prime plus 2 over xy is equal to natural log of x over x squared. Okay. Now this is in standard form. So we got p, that's 2 over x, and q, that's everything on the right-hand side. So let's go through step 1 and step 2 for integrating factor. So number 1, we find that integrating factor. Number 2, we write out the solution. So mu of x, that's e to the integral 2 over x dx. That's e to the 2 log x. That's e to the log x squared, so that's x squared. Okay. With enough, practice examples, you can skip all that middle stuff. If we have e to the integral 2 over x dx, your answer is just x squared. Okay. You do enough practice examples, you'll see the pattern with that. Okay, so we've got the mu. That's step 1 done. Step 2, we write out the solution as y of x is 1 over the mu that we found, integral mu of x, q of x dx. Okay, and remember the integral that comes with the plus c. So this is going to be 1 over x squared, the integral of x squared, natural log of x over x squared dx. And let's put our plus c just to be safe. Okay, x squared at the top, x squared at the bottom. That can go. So here we have 1 over x squared, integral natural log of x dx plus c. What's that integral? Don't forget the stuff from last semester. X log x minus x. Good. So 1 over x squared, x log x minus x plus c. And we're done. Okay, please do not forget the stuff we did last semester. It'll come up quite a bit now. Okay, because remember, like when you do the separation of variables, you got the integral on the left and the right. Those integrals can be anything we've done last semester. The same thing here. This integral of mu of x times q of x, it can be anything that we covered last semester. It can be partial fractions, bar parts, u substitution, trig integral, it can be anything. Okay, please be prepared for that. Okay, and then for homework, try the Laplace transform way. A little bit more difficult, but you can try it out. However, if you see this log x or complicated functions on the right hand side, try avoid the Laplace transform. Okay, so those of you looking for your bonus marks, save it for the end of the test, and then you can try it out because it will be a bit longer. Okay. But if you do have the free time after the test, go for it. You can try it out. Any questions for this one? All good. Okay, number 3. We've got y prime plus 2xy is equal to x. Okay, again, we go through the usual steps. It is first order. Okay, so that's good. It is linear. So that's good. So we can use integrating factor. So that's already one method we can use. Can we use separation of variables? Okay, maybe if I write it like this. Yes, we can. Right? Because we can take out the x and then it will be 1 minus 2y. Okay, so we can use two methods. Now that we see we can use two methods, you can also use Laplace transform, but I'm not going to do that here. We'll do the two ways. Which one do you think is easier? Separation of variables or integrating factor? Okay, so you go with that one. You do that one first. If you have some time and you want to try the other one, you do that second. Right? Don't do the more difficult one first. That's silly. Do the easy way first, and then if you have time, do the other way. Okay, so separation of variables, and then we'll do the other one. So we've got y prime is x 1 minus 2y. So the y prime we're going to write as dy by dx, x 1 minus 2y. We take the y's to the one side, x's to the other side. So we have 1 over 1 minus 2y dy, x dx. And integrates. Okay, integral of the left, what do we get? Yeah, minus a half. Yeah. Okay, you should be doing that in one step. Okay, none of that u substitution stuff. That's for babies now. You do it in one step. Okay. No, we've done a whole semester of that. This you should be able to do without u substitution. Okay. So just a note with the time allocation for these problems. The time allocated assumes you are not doing u substitution. So if you do u substitution, that's time taken out of something else. Okay. And then this side, that's just 1/2 x squared plus c. Now you could leave it like this. That's perfectly fine. You get all your marks. Otherwise, you can then solve for y. Okay, but that's just some algebra stuff. I'll leave that for you to do. Okay, so that's the separation of variables way. Let's do it the linear way. So we've got y prime plus 2xy is equal to x. We check, is this in standard form? Yes, it is. We've got the p over here. And all this other stuff, that's going to be our q. Okay, so step 1, integrating factor, that will be e to the integral 2x dx. So that's e to the x squared. Okay. Again, if you have to think about that, already too slow. Okay. Integral of 2x, x squared. Okay, we've got the integrating factor. That's step 1. Step 2, we write out that solution, with that formula. That formula there. Okay, so y of x is 1 over mu of x integral mu of x q of x dx. Okay, something like that. Okay, so 1 over mu, we can write that as e to the minus x squared. Integral mu times q, so that's e to the x squared times x dx. And let's put our plus c just so we don't forget that later. Okay, e to the minus x squared. This integral, what's that going to be? Are you missing something? 2. No, not 2. Half. It's half, right? Because if we were to do a u substitution, it would be 2u equals 2x. Take the 2 over to the other side, it becomes a half. Okay, please make sure you're not making mistakes with that. Okay, so that's going to be, well, just a half because the exponentials cancel, plus c e to the minus x squared. Okay, now for homework, like I said earlier here, where is it? Sorry, the separation way. If you do it the separation way and you don't solve for y of x, you just leave it as whatever, like we had here, over there, like we have over there. If you do it another way, it might not look the same. Yeah. So here we haven't solved for y, but if you do it using an integrating factor, then it's always y equals something. So just check. Okay. Okay. Yeah, so here this is, okay, that's using the separation of variables. And we see we still have that natural log 1 minus 2y over there. But in the other case, this gives us the answer as y already. So, if you want to compare them, then in the pink box, you have to then solve for y, and then you can compare. Okay, so just keep a note of that. Any questions on these two ways? All good. Okay, last one for today. So we have y prime cos x minus y sine x is equal to 1, with y of 0 is 1. Okay, so we've got this. Let's see what we can do. So it is first order, so that's good. Is this linear? Yes, yep, it's linear. So we can use integrating factor. So that's already one method we can use. Is it separable? No, it's not separable. Okay, so we can't use that way. Can we use Laplace transform? Oh, we can. Yeah, you can try. Because the Laplace transform of cos and sine, we know what those are. So you can give it a go. It will be difficult, but you can try it out. So let's try it using the integrating factor. Okay, homework, you can try it the other way. Okay, is this in standard form to use the integrating factor? No, it's not, right? We got y prime times something. So this is going to be y prime divided through by cos. Okay, so now this is in standard form. So we can do step 1, find the integrating factor. Step 2, find y. Okay, so integrating factor, that will be e to minus integral tan x dx. That's e to the minus integral of tan. Then linsec, good. Okay. Then we can put the minus inside and we end up with cos. Okay. So the integrating factor, that's just going to be cos. Okay, so we can now write out the solution. So this will be 1 over the integrating factor, integral of the integrating factor times q. Okay, again, the formula is not given. Okay, you need to remember that. So this will be 1 over cos, integral of cos times, and what did we have for q? Q was sec. Yeah, sorry. Okay, and let's put the plus c just to be safe there. Cos times sec, was that? 1. Yeah. Okay, so we're going to have 1 over cos. That will just be x plus c. Okay, so you can leave it like that, or if you want to write it as x sec x plus c sec x. If you don't like the fraction, you can write it like that, but either way is fine. All right. Any questions for this last one? All good. Okay. So for the quiz next week, the MCQ part, that will be more theory based. So all of the terminology we went through. So, what does first order mean? What does separable mean? What's an integrating factor? Linearly independent, all those words we went through. So that will be for the MCQ part. And then the written part is just evaluate the differential equation. Okay. I don't tell you what method to use. You use whatever you need. If you do it 2 ways, you get 10 out of 5. You do it 3 ways, you get 15 out of 5. You know the usual. Okay. If you do get more than 100, then whatever extra you get, I'll carry over to the next quiz. Okay. Any questions on that? Okay. Do you have your groups for the group project? Hands up if you do not have a group yet. Up so I can see, please. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Well, there's 12 of you. It needs to be groups of 3. So find your partners. Okay. Please make sure you have your groups ready for that group project. Otherwise, you're working by yourself. Okay. I'm not putting you in groups on the day. You come in your groups or you work on your own.